the rule that survived every rewrite of physics. Every time physics reinvented itself, this rule remained. The theories changed, the equations evolved, but this one idea refused to disappear. To understand why this matters today, we need to look at how radically physics has transformed over time. Classical mechanics gave way to relativity. Determinism fractured into probability. Space and time merged. Particles blurred into fields. Almost everything we once trusted was rewritten. The revolutions were not minor adjustments, but fundamental reconceptions of reality. Newton's absolute space and time were replaced by Einstein's flexible space-time. The clockwork determinism of classical physics gave way to the inherent randomness of quantum mechanics. Discrete particles dissolved into continuous fields, then re-emerged as excitations of those fields. Each transformation upended core assumptions about how nature operates. Yet through every revolution, one principle stayed intact. No matter the framework, no matter the scale, it survived untouched. When old laws failed, this rule still held. When intuition collapsed, it quietly remained true. This was conservation, the principle that certain quantities remain constant through all changes and transformations. Energy, momentum, angular momentum, and charge were conserved across every physical process, regardless of how those processes were described or what theoretical framework was used to analyze them. No experiment ever violated these conservation laws. No theory could afford to abandon them. At first, this persistence felt trivial. Of course, some principles would carry over, but as changes stacked up, the survival became suspicious. Why this rule? Why not others? Why did it remain valid even when the meaning of space, time, and matter changed completely? Other principles that seemed equally fundamental were abandoned as physics progressed. Absolute simultaneity vanished with relativity. Deterministic trajectories disappeared with quantum mechanics. The separability of space and time dissolved. Yet, conservation persisted unchanged, adapting its expression to each new framework while maintaining its essential character. The first hint came when physicists noticed something strange. Different theories describe reality in incompatible ways, yet they all agreed on certain outcomes. No matter how reality was modeled, this rule enforced the same constraint. It was not tied to a picture of the universe. It was deeper than the pictures themselves. Classical mechanics described conservation through deterministic trajectories. Quantum mechanics expressed it through probabilistic wave functions. Relativity incorporated it into the geometry of space-time. Despite these radically different mathematical structures, conservation remained a non-negotiable requirement in every case. This suggested a disturbing possibility. The rule was not a consequence of physics. Physics was a consequence of the rule. Perhaps conservation was not derived from deeper principles, but was itself the deepest principle, a constraint that any coherent physical theory had to respect. Physics might be the art of finding frameworks that satisfy conservation while describing observed phenomena. The rule came first, the theories followed, and once that idea surfaced, the rule stopped looking like a law among others. It began to look like a boundary that no theory could cross. Conservation was not a feature that could be added or removed from physical theories. It was a requirement for those theories to make sense at all. Any framework that violated conservation would produce contradictions, making prediction impossible and rendering the theory useless. At first, this rule appeared in the most familiar places. In motion, something was conserved. In collisions, totals balanced. In change, nothing truly vanished. The details differed, but the accounting never failed. When two billiard balls collided, their total momentum before and after remained identical. When chemical reactions occurred, mass and energy were conserved. When systems evolved over time, certain quantities remained fixed. These observations were so reliable that they became foundational to how physics explained natural processes. Classical physics framed it in one way. Relativity reshaped it. Quantum theory reinterpreted it. Each time, the language changed. The mathematics shifted. But the core demand remained the same. The universe did not allow imbalance. In classical mechanics, conservation laws were expressed through differential equations governing particle trajectories. In special relativity, energy and momentum merged into a four-vector that was conserved in all reference frames. In quantum mechanics, conservation became associated with symmetries of the wave function and was expressed through commutation relations. The formalism evolved, but the principle remained inviolate. When forces were redefined, the rule adapted. When particles replaced objects, it persisted. Even when reality became probabilistic, the rule held statistically. Outcomes varied, but the totals did not. The universe permitted uncertainty, but not violation. Individual quantum measurements might be random, but the statistical distributions they produced always conserved the appropriate quantities. A particle's position and momentum might both be uncertain, but their combined energy remained precisely defined. Conservation transcended the shift from determinism to probability. This created a quiet tension. Other principles were optional. They worked until they didn't. This one never broke. It did not care how reality was described. It only cared that the books balanced. Absolute space was abandoned. Instantaneous action at a distance was rejected. The continuous nature of trajectories was questioned. But conservation stood firm. It was tested in every conceivable way, at cosmic scales and quantum scales, in extreme conditions and mundane ones, and never once failed. As theories grew stranger, the rule became more abstract. It was no longer about obvious quantities. It became tied to symmetry, invariance, and deep structure. But abstraction did not weaken it. It made it stronger. The more general the theory, the more essential the rule became. Emmy Noether's theorem revealed the profound connection between symmetries and conservation laws. Conservation of energy arose from time symmetry. Conservation of momentum arose from spatial uniformity. Conservation of angular momentum arose from rotational symmetry. The rule was not arbitrary, but emerged from the most fundamental properties of space and time themselves. Emotionally, this was reassuring and unsettling at the same time. Everything else could change. Space could bend, time could slow, particles could blur into probabilities. But this rule remained unmoved. It provided a stable anchor in a sea of revolutionary changes. Yet its very immutability was eerie. Why should this particular principle be so privileged? What made conservation special when so many other seemingly fundamental ideas proved revisable? It suggested that beneath all the rewriting, there was something the universe refused to negotiate, and understanding that refusal was leading physics toward a deeper confrontation with what can never be different. Conservation was not just another physical law, but a structural requirement for any possible universe that could support coherent processes and meaningful evolution. The conflict sharpened when physicists asked why this rule survived when so many others failed. It was not protected by tradition. It was tested relentlessly. Every new framework tried to replace it, generalize it, or derive it from something deeper. None succeeded. Instead, conservation proved to be the bedrock upon which other principles rested. Attempts to construct theories that violated conservation invariably produced logical contradictions, or made predictions that conflicted with observations. The rule was not arbitrary convention, but necessary truth. Instead, the opposite happened. The rule began to explain other laws. Conservation emerged not as a coincidence, but as a consequence of symmetry. When time behaved consistently, energy was conserved. When space behaved uniformly, momentum held. The rule was not sitting on top of physics. It was holding physics together. Noether's theorem made this explicit. Every continuous symmetry of nature's laws corresponded to a conserved quantity. Conservation was not one law among many, but the shadow cast by the symmetries that made physical law possible in the first place. This buildup revealed something unsettling. Laws could change form, but the conditions that made them possible could not. Break this rule, and prediction collapsed. Cause and effect lost coherence. Reality stopped adding up. Without conservation, tracking the evolution of systems would be impossible. Energy could appear or disappear spontaneously, making outcomes unpredictable. Momentum could vanish without trace, making motion incomprehensible. The entire edifice of physics rested on the foundation that certain quantities remain constant, allowing us to connect past states to future ones through chains of reasoning. Emotionally, this was humbling. The dream of a final theory often imagined replacing old principles with deeper ones. But this rule refused replacement. It did not sit at the surface. It defined the boundary of sense itself. Conservation was not something that might be superseded by a more fundamental insight. It was the insight, the precondition for having any physics at all. To abandon conservation would not mean discovering a deeper theory, but abandoning the possibility of coherent theory altogether. As theories grew more abstract, the rule became less visible but more powerful. It operated silently, ensuring that even probabilistic worlds remained balanced. The universe could be strange, but it could not be inconsistent. Conservation worked behind the scenes, constraining which quantum states could exist, which processes could occur, which interactions were possible. It shaped the structure of physical law without always being explicitly mentioned. By this point, the question had shifted. It was no longer why this rule survived. It was whether any possible universe could exist without it. And that realization was leading toward a final, unavoidable conclusion. Perhaps conservation was not contingent, not something that happened to be true of our universe, but could have been otherwise. Perhaps it was necessary, built into the very concept of a coherent, law-governed reality. The climax of this story is the realization that this rule did not survive by accident. It survived because without it, reality cannot function. Conservation is not a feature of physics, but a requirement for physics to exist. Without conserved quantities, there will be no way to track change, no way to predict outcomes, no way to connect causes to effects. The universe would dissolve into incoherence. Once this becomes clear, the rule stops looking like a law and starts looking like a requirement. A universe without it would not merely behave differently. It would be incoherent. Events would not balance. Processes would not resolve. Prediction would collapse into contradiction. If energy could spontaneously appear or disappear without constraint, then every prediction would be meaningless because outcomes could deviate arbitrarily from what equations suggested. If momentum was not conserved, then isolated systems could spontaneously accelerate without cause. The fabric of causality itself would unravel. This is why every rewrite of physics preserved it. Classical mechanics needed it to explain motion. Relativity needed it to preserve space-time order. Quantum theory needed it to keep probabilities meaningful. Even when certainty vanished, balance remained. Each new framework had to incorporate conservation, not as an optional feature, but as a fundamental requirement. Theories that violated conservation were not wrong in some empirical sense. They were incoherent, unable to make definite predictions or maintain logical consistency. The universe allows uncertainty, flexibility, and variation, but it does not allow inconsistency. This rule is the price of coherence. It ensures that change never becomes chaos, that randomness never becomes nonsense, that complexity never loses its footing. Conservation draws the line between a universe that can be understood, where patterns persist and predictions work, and one that will be fundamentally unintelligible. Today, this principle quietly governs everything, from particles colliding to stars burning, from information processing to cosmic expansion. It does not announce itself. It simply enforces order beneath every transformation. Conservation laws constrain particle interactions and accelerators, govern stellar evolution across billions of years, shape the formation of galaxies, and determine which chemical reactions can occur. Every physical process respects conservation, making the universe predictable and comprehensible despite its vast complexity. The rule that survived every rewrite of physics was never negotiable. It was a condition that made rewriting possible in the first place. Everything else could evolve because this did not. Physics could abandon absolute space, determinism, and classical continuity precisely because conservation remained intact, providing a stable foundation upon which new frameworks could be built. The revolutions in physics were possible only because conservation was preserved through them. Understanding this does not make the universe feel smaller. It makes it more constrained, more precise, and more honest. Reality is flexible, but it is not careless. It allows many stories, but they must all add up. The universe grants enormous freedom in how processes unfold, what forms matter takes, how complexity emerges, but always within the strict constraints imposed by conservation. This combination of flexibility and constraint is what makes the universe both interesting and intelligible. Subscribe to join the journey. The rule